Oh, guess we can start. Hey, last class before spring break. Last Algebra I class anyway. Psalm 119 verse 97. Oh, how love I thy law. It is my meditation all the day. Let's pray. Father in heaven, yes, may we truly love your law as we ought and meditate on it all day, all night, whenever we have opportunity. Help us to be thinking about you, thinking of your word, striving in all that we do to please you, and including with what we do right now with this class time. Pray that you bless it, help us to use it well, and go with each student in this class over the break, and take care of us and our families, and that and bring us back together again after break. Thank you. In Jesus' name, amen. All right, please put your homework score into the Q&A box. You don't need to show me your papers today. Any questions on anything before we get started on the next piece? No new quiz or test coming your way today, so we do have a lesson note and a homework assignment, and I want to get started on that unless there are questions. If there are no questions, just make sure you have put something into the Q&A box, please, and let's get this party started. Okay, so let me remind you of something you already know. Well, first of all, what's the answer to this problem? What is x equal to? You know it's 4, right? Because that's the only number that we could put in that place to get a true statement. I mean, you could put all kinds of things in for x if you want, but you're going to get false statements every time unless what you put in for x is 4. So the only way you're going to get a true statement is if you put a 4 in here where x is, right? We know the answer is 4. And I have taught you, or you've learned, that you can multiply both sides of an equation by something as long as it's the same something, and it won't change the answer to this whole thing. As a matter of fact, let's just do it right now. Let's multiply both sides by 5, let's say. Okay, so now I'm going to distribute the 5 on the left side, and I get 5x plus 15 equals 35. If we subtract 15 from both sides, and I get 5x equals 20. I divide both sides by 5, and the answer turns out to be x equals what? What? What's 20 divided by 5? It's the same answer, crying out loud. It did not change. Even though I multiplied both sides by some number, it didn't change the answer. It's still 4. 4, 4, 4. That's it. Okay, so, ladies and gentlemen, it turns out that same rule can be used even if it's not an equation, even if it's an inequality. Remember inequalities, greater than, less than? Those are inequalities. So, if we have a problem like x is greater than 3, let's say, what numbers can we plug in for x that would make this true? I could plug in a 4. What else? 5? Yep. Anything higher than 3, Max says. 4, 5, 6, 7, 8, 9. Anybody want to say 10? Oh, good, we got a 10. Anybody want to say 300? Or 472.069? Anybody want to say 3.1? 3.00000000001? Because that's greater than 3, right? There's a bunch of numbers we can put in here, of course. You could even put numbers in that are lower. There you go, Max. Even that is greater than 3. We could put numbers in there that are lower than 3, but it wouldn't be true. We'd be lying. We'd be making a false statement. So check this out. The same rule applies. You can multiply both sides of an inequality by the same thing, and it won't change the truth value of it. Check this out. Okay, here we go. Now we got 5 times x is greater than 15. Now can I put something in lower than 3? Let's try a 2. If you put a 2 in for x, what you get is 10 is greater than 15. Well, that's false. Nope, that doesn't work. Can we put a 4 in there? Let's see, 20 is greater than 15. Hey, that's true. You see, it's the same answers. And if I divide both sides by 5, I'm back to x is greater than 3 again. See, it didn't change it just because we multiplied both sides by the same thing. So that's the point of the first part of today's lesson is, well, that's one of the points. We actually have 4 different things to talk about today. The first one is that you can use the same rule with inequalities that we use with equations that says I can multiply both sides of an inequality by the same thing. It doesn't change the solution to it. I can also add or subtract the same thing on both sides of an inequality. It doesn't change the solution to it. Okay, just like with equations. With equations, you can add or subtract the same thing to both sides. You can multiply or divide both sides by the same thing. It doesn't change the answer. And the same is true with inequalities. Doesn't that make life simple? No, I didn't freeze. Ha! I didn't freeze. The point, I'm just pausing for effect, because actually there's a little catch to all this. There is a catch to all this. It would be nice if we could just stop there and say, yeah, same rules for inequalities as equations. Same rule. Well, not entirely true. I mean, most of that's true. About everything I've said so far is true. Everything I've said so far is true. Except, well, let's go back a bit. What was that problem we had up here a moment ago? X plus 3 equals 7 or something. Let's do this. Let's do this. So here's that same problem we had before. You know the answer is 4. This time, I'm going to multiply both sides by, say, negative 2. I'm going to multiply both sides by negative 2. Okay? So there we go. Let's see here. So that'd give us negative 2x minus 6 equals negative 14. Add 6 to both sides. Add 6 to both sides. And I get negative 2x equals negative 8. Negative 8. Divide both sides by negative 2, and what do you know? Sure enough, x equals 4. Yep. So, what's new, Mr. Rauch? No, that's not, we already knew we could do that. Multiply both sides by the same thing. And the answer doesn't change, it's still 4. Yeah, but check this out. What was that inequality I had a moment ago? Wasn't it something like x is greater than 3 or something? X is greater than 3 or something. Okay, let's now multiply both sides of this by -2. -2. And so now what I get is negative 2x is greater than -6. Divide both sides by -2, -2, -2, -2. Wait a minute, let's stop right here. Actually, let's stop right here. Let's stop right here. I'm thinking, don't go away. Don't go away. What? Oh, I know. Yeah, I should have set this up a little different. So we know right now that like there's a bunch of answers, right? 4, 5, 6, 7, and so on. Let's just put a 5 in here for x. So I put a 5. I took the x away and put a 5 there, right? Okay, and so this, and sure enough, it's true, isn't it? 5 is greater than 3. That makes total sense. But now watch what happens when I multiply both sides by -2. I get -10 is greater than -6. Is that true? Don't forget that by greater than, we mean that any number on the number line that is to the right of another number is greater than that number. Any number that's to the right of another number is greater than that other number. Is -10 to the right of -6? No. -10 would be like here, and -6 would be like here. -6 is to the right. Therefore, -6 is greater than -10. But look at this. Look at that. That's a false statement. It's saying -10 is greater than -6. Now, what in the world is going on, Mr. Rauch? I thought we were doing so well. Everything you did on the screen made total sense, and it was all review. Most of it was review anyway, and so I was kind of tempted to not even really pay full attention to you, and now something goofy has just happened. What did you must have snuck something in on me while I was yawning or something. No. Here's what happened. Here's the catch. Remember I said, look, all the same things that apply to equations apply to inequalities. Except, there is a catch. Whenever you multiply or divide both sides of an inequality, whenever you multiply or divide both sides of an inequality by a negative number, like I did just now, -2, I multiplied both sides by -2, you have to flip the symbol. That greater than symbol has to become a less than symbol. And then everything will still be true. You hear me? You get that? Did you follow that? Notice these symbols are not the same. One is a greater than, the other is a less than. You have to flip the symbol. Whenever you multiply or divide both sides of an inequality by a negative number, if you multiply both sides by a positive number, don't flip the symbol. Okay, let's go back. Let's go back. What if I multiply both sides by +2? Okay, then I get 10 is greater than 6. That's still true. That's all fine and good. No flipping or anything. You can multiply both sides or divide both sides of an inequality by the same thing, totally okay. But if you multiply and divide both sides by a negative number, you gotta flip the symbol. You gotta flip the symbol. It's gotta be flipped. Flip it, man. If you're gonna if you are going to multiply both sides by a negative number, you got to flip the symbol. And then everything will still be true. Okay? Yes. Whenever you multiply or divide both sides by of an inequality by a negative number, you got to flip the symbol. You could say that for equations too, by the way. Right? If you had something like 2 plus 3 equals 5, and then I multiply both sides by negative 2, so you get negative 4 minus 6 and negative 10 over here. You can go ahead and flip the equation, the equal sign. Go ahead, flip it. There, I flipped it. Okay. Right, it doesn't really make much. It doesn't make much difference if you flip an equal sign, because it looks the same. Okay, I'm just kind of being silly there. But you need to remember that with inequalities, anytime you multiply most times by a negative number, you got to flip the symbol. Let's look at 1 or 2 examples here where we actually graph the answer on a number line. Okay, is that okay? If I go, let me go grab my number line. Number line. Where are you? I need you now. I found it. Hey, I found it. Hey guys, I found Fido. Hey guys. Okay, anyway, I'm getting distracted. Let's take a look at something. Yeah. How about this one? Ooh, yeah, let's look at this one. Okay, so, they want us to graph the solution to this. 4 minus x is less than or equal to 6. And then they tell us that the domain is integers only. Okie dokie smoky. Let's subtract 4 from both sides. We don't flip the symbol just because you're subtracting or adding a negative number. Whenever you add or subtract a negative number both sides, you don't flip the symbol. It's only when you multiply or divide. Okay? So if I add a negative 4 to both sides, I get negative x is less than or equal to 2. So I have not flipped the symbol, because adding a negative number doesn't mean you flip the symbol. It's only multiplying or dividing. Well, as you can see right now, I got negative x is less than or equal to 2. I don't want that to be negative. So I'll multiply both sides by negative 1. Or you could think of dividing both sides by negative 1. Either way. When we multiply or divide both sides by negative 1, we have to flip the symbol around. And there we go. Now x is greater than or equal to negative 2. You see that there? We flip the symbol here. Instead of less than or equal to, it's now greater than or equal to. And now I can go start to graph this. And according to my domain there, I'm only allowed to graph integers. So any integers that are greater than or equal to negative 2, I can graph those. So this one here, this one here, this one here, 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 and yeah, a bunch actually. Oh man, glad this number line isn't any longer. I'm getting tired of drawing these dots. And then I'll color the arrowhead here to indicate there's more integers to the right. And there you go. Any questions on that? Questions on that? Don't forget that rule. It's kind of easy to forget or get confused. Some people want to flip it when you add a negative number to both sides. No. Only when you multiply or divide both sides by a negative number. Also notice here, ladies and gentlemen, I notice here, I did multiply both sides of this by a negative number. I just didn't show it. Okay, I didn't show that step. So that's why I flipped the symbol here. Because the only way you can get from this to this, the only way you can get from here to there is by multiplying both sides by -1 or dividing both sides by -1. Either way, if you multiply or divide both sides by a negative number, you got to flip that symbol. Okay? I hope it all makes good sense to you because we got something totally different to talk about now. And that is finding the volume and surface area of spheres. Sphere. A sphere. You know what a sphere is. What's a simple word for another simple word for a sphere? Yeah, a ball, basically. That's right. A sphere is three-dimensional, not just two-dimensional. A circle is two-dimensional, okay? A circle is just flat, something flat. But a ball is three-dimensional, something you hold in your hand and toss up and down and throw and all that stuff. Yeah, three-dimensional circular object. Yeah, that'll work. Okay, so we're going to talk about finding the volume and surface area of a ball, a sphere, a ball, a sphere ball. Okay. I'm going to try to, of course I'm drawing on a two-dimensional screen here, but I'm going to try to make this look three-dimensional. Yikes. Does this remind anybody of anything? What's that remind you of? A basketball? Why would it remind you of a basketball? It's the exact reverse colors of a basketball. Because it's orange and black. But most basketballs are orange with black lines. This is a black basketball with orange lines. Anyway, so yeah, hopefully you see a ball there. So let's talk about this class party, a class party for our class. You already know the difference, hopefully, between surface area and volume. We're going to talk about surface area and volume, but let me remind you in the form of a story. So we were having this class party. Do you all remember that party we had? Remember that party we had over at Tori's house? Because her brother is the president of the Movies and Music Club, and Callie's hanging out there too. And so we said, let's have the party there. They seem like nice people. They'd host a big party. And so remember that party we had and we were all there? Well, all of us there except for Isaac. Isaac wasn't there, but the rest of us were there, and we were having a good time, and we were playing basketball out in the backyard, and we were having such a good time playing basketball we didn't want to quit. And so, but then it started getting dark, and Isaac still wasn't there. Matthew, maybe you were too drunk, huh? Drinking too much punch or something? Next time, lay off of that Mountain Dew, dude. Whatever. Anyway, just teasing. So we were all at this party, having a good time playing basketball. Yeah, that's not good. And it was starting to get dark, and we were like, what are we going to do? What are we going to do? Because we're still having a good time, and it's getting kind of hard to see. And thankfully, Ava, ever so resourceful, Ava pulls out of her back pocket something, and she's like, hey, I got this. And we're like, what is that? And so she says, give me the ball. And so we give her the ball, and she starts rubbing this glow-in-the-dark paint all over the ball. It's like, we can keep playing. It's like, you had glow-in-the-dark paint in your back pocket? Yeah. So, always carries it with her. Way to go, Ava. So, now we can keep playing, right? Well, how much paint did it take to cover the basketball? That's the idea behind surface area. That's the idea behind surface area. How much paint did we have to use to cover the outside of the ball? And if you want to paint the lines too, I could have painted the lines. Boom. But yeah, there you go. So now, totally covered the ball in glow-in-the-dark paint. However much paint it took, that's the surface area. Now, remember, Isaac hasn't shown up yet. But so we're playing around, and we're finally starting to maybe get enough playing in. We're starting to be played out a little bit. There goes Matthew again, walking away to go get some Mountain Dew. Dude, you've had 4 cans already. Yeah, just one more. I can handle one more. So we're like, okay, fine. You know, the game's kind of breaking up anyway. And hey, look. Isn't that Isaac driving around looking for a place to park? And so it was Olson's basketball, and he says, dude, I got an idea. So he says, give me the ball. And so while Isaac's finding a parking spot, Olson takes the ball and he goes over to Tori's sandbox, and he cuts a little hole in this ball and fills it up with sand. Right? So he fills the ball completely up with sand. Totally packed full of sand. Right? And how much sand did it take to fill up the ball? That's the idea behind volume. And then Isaac comes walking across the yard. Hey guys, sorry I'm late. And Olson says, hey Isaac, think fast. And he tosses him the ball, right? And Isaac thinks that this is just normal, glow-in-the-dark, light, airy basketball coming towards him. And when this basketball full of sand hits him, he's like, thunk, knocks him back like 4 feet, you know. What is in this thing? And Olson's like, that's what you get for being late, man. We're having a good time. And so, anyway, how much sand did it take to fill up the ball? That's the idea behind volume. Surface area is how much paint it takes to cover the outside. How much air can that ball hold inside, or how much sand can it hold inside, or how much water can it hold it inside? That's the idea behind volume. Okay? So you got the difference there between volume and surface area. All right, so now all we need are formulas for this. I'm just going to come right out and tell you, but then I'm going to show you some stuff to maybe help you remember these formulas. The surface area of a sphere. To find the surface area of a sphere, it's 4 pi r squared. To find the volume of a sphere, this one's a little trickier maybe, is 4/3 pi r cubed. 4 pi r squared and 4/3 pi r cubed. Those are the 2 formulas you need to know. If you want to find the volume of a sphere, is if I tell you what the radius of that ball is, the radius of course being from the center of the ball to the outside surface of the ball. If I tell you the radius of the ball, you just plug it into this formula here and you can find the volume. Or plug it into this formula here and you can find the surface area. Okay? So, now let me show you a couple things the book shows you. The book's kind of funny, I think, when it shows you this. The book's got a couple pictures. If you have your book open to page 380 and 381, let me go see if I even have this that I can just pull up on the screen. I probably don't. What is this? Lesson 91. Hey, I do. Praise the Lord, from whom all blessings flow. Hold on here. I'll just show you what I got. I'll show you what I got here on the screen as soon as my computer speeds up a little bit. this is really kind of funny, I think. At least I have a little fun making fun of this because the author in the textbook hello. Take your good old time. Thank you very much. I don't have time for you to decide to cooperate, machine. Come on. I wish something funny would have happened to me on the way to your class today. Thank you. 20 minutes later, here we are. Okay, can you see that? You see that picture of a ball inside of a round cylinder? It's inside of a cylinder. So I don't think he drew this real well, but it's probably nicer than what I would have done. There's notice that look at this right here. Look at what the author says right here. Close your eyes and try to remember this diagram. It sounds almost like he's saying, close your eyes and look at that picture. That's kind of what he says right there. Close your eyes and look at that picture. Wait a minute, Mr. Saxon, wouldn't it be easier to see it if we have our eyes open? Anyway, I think he wants you to look at the picture and then close your eyes and sort of remember that picture. Because if you could remember that picture, you can kind of come up with this formula for volume all on your own if you think carefully about it. Because all of us should already know the volume of a cylinder. The volume of a cylinder is the area of the base times the height. Well, the base on a cylinder happens to be a circle, right? So we know the area of the base. It's pi r squared. So pi r squared times the height. But in this case, since this cylinder happens to be exactly just barely tall enough, like if you go to the store and you tell the clerk, I want to buy this ball, and she says, oh, I have a nice box that can fit in. Would you like it? Great. Yes, thank you. Because it's a birthday present for Olson since he poked a hole in his ball and filled it up with sand. So, yeah, if you got a box to put it in that'll make it nice to wrap up, that'd be great. So, so she gets this round box, this cylindrical box. And when she puts the lid on, the lid barely touches the top of the ball. So that means the height of this ball, the height of the box is just two radiuses, isn't it? One radius up and one radius down. That gives us the height of the box. So I'm still over here talking about the volume of the cylinder. It's area of the base times the height. We know the area of the base is a circle, so it's pi r squared. And now we know the height is actually 2 times the radius. So in place of h, I can write 2r. Let me put the 2 in front. And so I have r squared times r, which is r cubed. And there we go. That's the volume of the box. But wait a minute, I'm trying to find the volume of the ball, not the box. And as you can clearly see, there's a little bit of empty space around the bottom of the ball and a little bit of empty space around the top. So obviously the ball is not totally filling up the box. As a matter of fact, the ball only takes up 2/3 of the box. So I need to multiply this formula by 2/3. Well, 2/3 times 2 pi r cubed is 4/3 pi r cubed. And there you go, ladies and gentlemen. That shows you where that formula comes from. Now, that took a little while. You just need to know the formula. But if you ever forget it, that's why the author is telling you, close your eyes and look at this picture. Or wait a minute. look at the picture and then close your eyes and think about it, because if you ever forget the formula, maybe you can do what I just did and recreate it. So if you ever forget, hopefully you can recreate it. It's 4/3 pi r cubed. And of course we know volume has to be in cubic units anyway. So so you ought to at least remember that there's an exponent of 3 on the volume formula. 4/3 pi r cubed. The ball takes up 2/3 of the box, which looks about right. So there you go. 2/3 times 2 pi r cubed is 4/3 pi r cubed. One other thing to show you, here it again. The author says, close your eyes and look at this picture. Okay, he doesn't quite say that, but it almost looks like he says that. This one's the surface area formula. He's basically showing you, look, if I had 4 flat circles with the same radius, we know a circle is 4 pi r squared. I'm sorry. We know a circle is pi r squared. And if you have 4 of them, pi r squared plus pi r squared plus pi r squared plus pi r squared, that's the same as just 4 times pi r squared, because we have pi r squared 4 times. So 4 times pi r squared will give you the surface area for this ball. It's the same as having 4 flat circles and finding their areas and adding them together. So again, if you ever forget this formula right here, 4 pi r squared, maybe remembering this picture will help you. Oh, that's right. It's just the same as 4 circles, 4 flat circles, which would just be 4 times pi r squared, right? Because everybody here hopefully remembers the formula for a flat circle is just pi r squared. Well, if you have 4 of them, you basically have the surface area of a sphere that has the same radius. So close your eyes and look at that picture, or whatever. Yeah, something like that. Yeah, you're not really supposed to say radius. This is, I just say it sometimes to so people know what I'm talking about. It's radii. Radii is plural for radius. Yeah, close your eyes and look at the picture. Look at the picture with your eyes closed. Miss, wouldn't it be easier if we opened our eyes? Miss, may I go out and do some breathing? Well, I hope you all have a great spring break. You may get a message or two from me if there's anything that you still need to turn in or retake or something like that. But other than that, have a great spring break, and Lord willing, we'll see you in a week and a half or something. A week from this Monday. You're welcome. See ya. Yep, see you tomorrow, Tori. Good question, Jude. I think I set it up to be due when you come back from spring break.